Okay, I think we are supposed to start. It's 1 o'clock sharp. So, yes, good afternoon. Welcome back from lunch. This is the fourth candidate mission, CryoRad. My name is Matthias Drusch. I'm the mission scientist from ESA, looking after the mission in phase 0. So first of all, maybe a few words on phase 0. So phase 0 work normally is about to make sure that the requirements we have are understood by scientists, also industry and engineers. Very often we do not speak the same language. And of course we need to establish traceability between scientific goals and mission requirements. So this is what it's all about. Then in addition, science normally starts a long time before mission launch. So ideally for an Earth explorer, you have new discoveries, new science during all implementation phases, and even before you submit the proposal. So for CryoRad, we had to develop new radiative transfer models, making new measurement devices for dielectric properties, a new airborne demonstrator certification for this demonstrator, first flights, and then consolidating the requirements. And this all will be presented by the MAG. So you see the MAG and my ESA colleagues on these slides. I'm not going to read all the names. They will introduce themselves. And before, and as for the candidates before, this is only a small selection. There are many PhD students, master students, postdocs who contributed who are not on the slide. I hope they are online. And I hope they follow this discussion as well. And with this, I think we can start with the introduction to the mission. First of all, I would like to introduce Anne. Anne will guide us through, let's say, the top-level traceability from guiding science questions down to mission objectives. So, Anne, please, your floor is yours.
All right, thank you. I think I want to go a bit about this one. All right, so yeah, my name is Anne Solgaard, and I will be giving you an introduction to the CryoRad mission through the guiding science questions and mission objectives. But I will start out with giving you some of the highlights of the mission. So the tagline for CryoRad is delving deep into ice sheets, and that is exactly what CryoRad will do. It will penetrate all the way through the ice sheets and for the first time retrieve the temperatures inside the ice sheet from the base to the surface of the ice sheet. And how is this possible? It's because CryoRad is the first ever hyperspectral radiometer in P-band and L-band, so it covers the spectrum you see in red. Down here, it's in gigahertz, the unit is missing. And then you have in blue existing passive radiometer missions. So this, having this white band opens for a whole new window of observations. So CryoRad focuses on components of the polar climate and will be able to also measure the thickness of the growing sea ice, as well as the salinity of in cold waters. And throughout the presentation, you will see these different symbols on the slides, indicating which of the key components we are talking about. And then it should also become clear that even though there are 3 separate components, they interact and they have feedbacks between each other. And the changes that we see happening to the components, they have not only local implications, but implications for global climate. All right, so with this in mind, the data sets that we are going to be able to provide with CryoRad will contribute to several of the ESA science strategy questions. So for the ice sheets, this will help us better understand the processes that govern the flow of the ice sheets, and this will then help constrain and help us predict what sea level rise will be in the future. This is important for all of us living in coastal cities around the globe. It will also help us guide our understanding of the glacial isostatic adjustment. Being able to measure the sea ice, or the growing sea ice thickness, will help us better understand the physical processes that govern the sea ice state and variability. And this will also help us understand how the polar regions have impact on the global climate. And for the sea surface salinity, this is an important component to have in the polar oceans in order to be able to learn about the ocean carbon cycle. It also helps us understand the interaction and fluxes between the coastal regions, between the atmosphere, the land, and the sea ice. And so with this in mind, these different science questions, they contribute to 5 of the overarching science themes within the strategy. If we look at the tipping points in the Earth's climate, so these are tipping points is when you cross a line and something becomes irreversible and brings on a very large change. The data sets from CryoRad will also help with observations so we can learn more about these tipping points. So for ice sheets, this is when the ice sheets disappear and cannot readily grow back. This has implications for freshwater into the ocean. Same for sea ice. If the sea ice disappears, our data set can help us understand the processes that govern this. This has also implications for albedo and for stratification in the oceans. The sea surface salinity is a good input to understanding how the overturning circulation works, and this is important for us living in Europe with the climate. The secondary mission objectives also have data that can help us learn about the permafrost when it will disappear, and the same for vegetation when the boreal forest will change. So with these things, now we can go into a little more detail and look into the 3 different components that we focus on with CryoRad. So the overarching goal of CryoRad is to contribute to a better understanding of the polar processes in a warming climate from the interior of the ice sheets to the open oceans. So the focus is really here on providing data sets that can help us understand the processes that are important in the climate system. And from the presentation this morning, there was a very nice introduction to the warming of the climate. The climate in the polar regions is also warming. It's warming 2 to 4 times faster than the global average, and this of course impacts processes in the polar regions. And in the figure here on the bottom of the slide shows the example from the Arctic region. So if we then focus on the different components, if we look at the ice sheet, the figure shows observed ice sheet mass loss. It's from IMBI, so it's a community assessment of different observational data sets of ice sheet mass loss. You have time on the bottom from the 90s and onwards. You have mass change in gigatons on the left, and you have the equivalent sea level contribution on the right. And in blue and in purple, we have the Greenland and the Antarctic ice sheets. And as you can see, they have contributed, they have accelerated their mass loss since the beginning of the 90s. Currently, the Greenland ice sheet is the largest land contributor to a land ice contributor to sea level rise, and the ice sheets also constitute a very significant part of the sea level rise. So when the ice melts or disappears from the ice sheet, it enters the ocean through surface runoff and through calving at the front. And it then enters into the ocean, delivering fresh water to the system. If we look at the sea ice has also been declining. Sea ice extent and sea ice volume has declined. And sea ice has become, in general, younger over the past decades and thinner. And this is what the figure here on the right shows, but it shows also for the Arctic in the top and for the Antarctic on the bottom. But it also shows that it has varied a lot between the different hemispheres. So what we see in the Arctic, we see this is since the 90s, and this is the winter mean volume anomaly of sea ice shows there was a large decline in the Arctic sea ice volume up till around 2010. And since then, there has been no really loss of the Arctic sea ice volume, although you see there has been a huge variability. If we go to the Southern Ocean, to the Antarctic, then just prior to 2015, there was actually an expansion of sea ice, then followed by a rapid loss of sea ice volume, so entering a new regime. And this does not work. Oh, sorry. Okay. If we then turn our attention to the freshwater cycle in the oceans, we have now seen that when sea ice melts, it contributes to freshwater into the oceans. When the ice sheets lose mass, they also contribute freshwater into the ocean, so adding to the freshwater. But also we know that there has been an increase in the input from rivers and from precipitation events into the Arctic. And this graph here on the right shows for the Arctic Ocean, on the left, the integrated steric anomaly from satellite altimetry over the Arctic Ocean, as well as in situ measurements of the freshwater content. And it shows that in recent decades, this is what we observed. There has been an increase in freshwater input. And this is important in the polar oceans because they are driven by salinity, so changes to that impacts the seawater density and thus the stratification as well as the circulation. So this also has implications both on the local and on the global climate. So with these changes in mind, this brings us to our guiding science questions. So for the first one, relating to to ice sheets and sea level rise. So the guiding science question is, how do internal and basal processes within ice sheets and ice shelves control their stability and long-term contribution to global sea level rise? For the sea ice state, which processes control sea ice state and variability? And the third guiding science question relates to the freshwater cycle. So how do changes in freshwater fluxes at higher latitudes impact large-scale ocean dynamics and influence global climate patterns? And we will now look into how the data sets or the measurements that we can provide with CryoRad can help answer these questions. Answer these questions. So if we turn again our attention to the ice sheets, we saw before from the INBI assessment of the mass loss from the ice sheet that has been a decline, and this is actually the same data we are seeing here now in blue, but as a cumulative mass change since 2015. What you should also have a look at is then the gray that comes from models. And if we then take a look at what happens after 2015, you see a very large spread in what the models predict. And what you should take from this figure is that at the moment, ice sheet models, they struggle in actually capturing the trend that we see from observations in mass loss, and they also disagree on what happens in the future. That's a large spread. And where does this spread come from? It comes, of course, from the forcing, from the ocean forcing, from the climate forcing, but it also comes from uncertainties in the model, so how we understand processes and how we parameterize them, as well as important observational gaps of data sets that can help initialize and constrain the ice sheet model. And one example of this is exactly the ice sheet temperature. It's not been measured before. We only know it at a few boreholes around the ice sheets. And it plays an important role, ice sheet temperature, in how the ice flows. So this is a cross-section of an ice sheet from the interior out to the ocean. In gray, we show the velocity profile through the ice sheet. And in the blue and red, we have indicated areas that could have where the ice is frozen to the bedrock, and in red places where the ice is thawed at the bedrock. And where it's frozen to the bedrock, the movement is by deformation. So ice is a viscous fluid. It deforms under its own weight due to gravity. And how fast it deforms depends on temperature, because a higher temperature will lead to a lower viscosity and then increase deformation rates. If we then also have areas with sliding, this will then help move the entire ice column. And in the places where there's sliding is often constitutes a very important part of the total velocity at the surface. So, as I said, we don't really know the temperature within the ice sheets. We can simulate it using past climate and geothermal flux. And also just what is happening at the base, what is the basal thermal state, is also to a large degree unknown. So this is from models, and it's a little bit of a confusing figure, but what you should take away is that models agree on where the ice is melting at the base when it's bright red, and they agree that they're frozen in areas where it's bright blue. And areas in between are areas where we don't have a total agreement. If we then turn the attention to the sea ice thickness, then you saw before that since 2010 in the Arctic, there has been no further ice loss of volume. And this is thought to be because of the thin sea ice that's now present is interact or goes into a negative feedback actually because it's so thin, then it can make, when the climate is cold and the ocean is cold, you can have sea ice growing. However, in the future, what we're looking into is a warmer climate and warmer oceans, so this feedback will, negative feedback will stop, and the sea ice thickness will decline and the sea ice will disappear. So it's important to be able to measure this thin sea ice in order to understand this process that's going on at the moment. For sea surface salinity, we saw before how that in the recent decades we have had added fresh water to the Arctic. This is important for the surface stratification and mixing. If we look here on the right hand, we have the present condition. We have the sea ice that sort of protects the upper surface layers of the ocean from mixing and from interaction with the atmosphere. However, what we're looking into is a situation with no sea ice in the Arctic, or less sea ice, so there would be a larger degree of mixing, degassing from the ocean, or interaction or gas exchange with the ocean, heat entering, so become more like the Atlantic, at the same time with the competing effect of the melting ice sheets and melting sea ice that will contribute freshwater layer. So it's important to understand these processes, and for that we need to be able to measure the salinity in these areas, in the polar regions. All right, so with this I will introduce the primary mission objectives. So the first one is that for ice sheet temperature we shall measure the temperature with an uncertainty better than 1.5 Kelvin. This is for the glacial temperature, and we will also assess the thermal state of the bedrock. And this is, just to say it again, it's the first time that we're able to measure the temperature within the ice sheet. For the second primary objectives, we shall measure the sea ice thickness with an uncertainty better than 20% for growing ice between 0.5 meter and 1 meter. This is an unprecedented accuracy for thin sea ice. And lastly, we will measure sea surface salinity with an uncertainty below 0.3 pss in cold waters, and that's below 278 Kelvin. And this is also that CryoRad will have an unprecedented sensitivity to sea surface salinity in the polar regions. And with this, I will hand over to Steph, who will talk about the mission requirements.
Thank you, Anna. I'm Stef Lemit. We focus on remote sensing of polar ice sheet and ice shelf processes. And my goal in the next 10 minutes is to translate the very clear science questions we had into what drives our mission now. And to do that, I think it's important to remind what CryoRad actually is. So there's this wideband radiometer, which goes from P band to L band, and it's hyperspectral, so it has these very narrow channels. And by being a radiometer, it measures the radiation coming from the surface. So it measures brightness temperatures. And that brightness temperature is dependent on both the emissivity and the temperature of the Earth's surface. Now, both this emissivity and temperature are key components to our mission. And they behave a bit differently for the different mission objectives. If you look at the ice sheet temperature, we really see that the brightness temperature as a function of the frequency really depends on the temperature. So if we have very short frequencies, low frequencies, we can penetrate up to the base. If we have longer frequency, if we have shorter wavelengths, we see the top. So there's really the relationship between brightness, temperature, and temperature. Whereas if we go to the sea ice thickness, sea ice thickness is really a function of the emissivity changes as a function of the sea ice thickness, the same with our salinity measurements. There we really look at changes in emissivity. And if we now look at our first baby, the ice sheet, you really see this already illustrated. What you see here is the emission depth, so where in the ice sheet the radiation is coming from as a function of the frequency and the ice temperature. And so you see, for example, here at the smallest frequencies, depending on the ice sheet temperature, we can look a bit deeper than 1,000 meters for these very cold ice sheets. However, at the same time, if you look at this figure, you see that the emission depth increases with lower frequencies. So if we have lower frequencies, we can look deeper into the ice. Another important thing to realize here is that we have also plotted the mean thicknesses and the maximum thicknesses for both Greenland and Antarctica. And what you might notice, for example, is that for large parts of Antarctica, with the smallest frequency, we are not able to see the bottom. So that's why we actually need this frequency range. We don't do this frequency range because we like it, it's because we need it. And so this brings us to our first, and I think unique requirement, is that CryoRad mission shall have this frequency range between 0.4 and 2 gigahertz. Our second requirement relates to our coverage. We are a global mission. We will have measurements over the entire globe, but our focus is on these polar regions where we need where we need complete coverage. So we don't want a polar hole, and where we want enough overpasses, for example, to measure the changes in salinity. So this brings us to our second requirement, that we should have this complete coverage over this 50 degrees polewards region. Our third requirement is related to the spatial resolution. I think it was already said before, but currently the ice sheet temperatures are rather unknown. We rely on sparse borehole measurements. You see them depicted here as the red dots. If we would make a map of Antarctica, it would even look much sparser. So we rely on these very few measurements. At the same time, if we look at how the uncertainty of these temperatures is in the models, and we do that at 100-kilometer resolution, you see that the standard deviations are high, that we basically have a very high uncertainty in our models. And with 100-kilometer resolution, we are not really able to discriminate between the different basins or between the different dynamic processes. So therefore, we made the requirement that our resolution should be 50 kilometers or better. That's our requirement to be able to resolve these processes. Because then we can really start to fine-tune and understand and better the models. Then we come to observation requirements. And I think here it's important that these observation requirements are driven by scientific uncertainty. I'll address them here for each PMO, but this is really our scientific uncertainty that drives what we need. And you see this here, first illustrated for the Greenland ice sheet. You see the difference between the left and the right figure, and the colors indicate where the bed is temperate, so where the ice is sliding over the surface. And the first thing you might notice is that there's a very big difference between the figure on the left and the figure on the right. That basically means that the models very strongly disagree, or that the initialization is very different between two different parameterizations. The second thing you see is that there's subtle but important differences between the red, the orange, and the yellow. And these differences in color come by sensitivity experiments we did. But like, what if we change the temperatures? What does it mean in terms of being temperate or not? And these differences to us show that we should have a 1.5, our uncertainty should be smaller than 1.5 Kelvin if we really want to make a difference here. The same goes for the sea ice thickness. What you see on the right is the current uncertainties we have for existing and, for example, the future or the planned crystal mission. And you see, for example, that with SMOS, we can get very good uncertainties for the very thin sea ice. At the same time, with CryoSat and with crystal, we can get good uncertainties for the very thick ice. But there is actually this gap here where in this this very important sea ice thickness, which is the growing sea ice, where we have currently very large uncertainties. And that made us drive us to this requirement that with CryoRad, we want to fill this scientifically important gap to get better occurrences there. And that's why we came up with this observation requirement of having an uncertainty of below 20% for growing sea ice in this sea ice region up to 1 meter thick. That brings me to our third PMO for salinity. What you see here on the right is the standard deviation between the models in salinity. And I'll show it as an animation in a second. And what you see on the color bar is the standard deviation. So basically everything that's green or red are regions where the models strongly disagree in salinity measures. And if I now start playing this animation, you see it's a bit grayed-eyed where the sea ice is. You will see that actually these polar regions with cold waters, this is the region where the models strongly disagree in salinity measures. You see it somehow differently also depicted in this figure. This is a 2D histogram. And so you see that the uncertainty between the models, standard deviation, is rather low for warm water, but we have this region here where everywhere where we have very cold waters, we see a very strong standard deviation between the models. And that line, that gap, has driven us to observation requirement number 3, that we should have surface salinity estimates with an uncertainty below 0.3. So these are our requirements. Now, how do they now translate into measurement requirements? The ESA technical team in a couple of minutes will explain how they make it happen, but how do they translate? So I said we need this spatial resolution of 50 kilometers. We want this polar coverage of 50 degrees polewards. These, in our phase 0 studies, translated in a spatial resolution we would have we would need of 50 kilometers at 0.4 gigahertz, and even better at higher frequencies. We also need overlap to make that happen, and we need a revisit time to be able, for example, to measure the changes in salinity. Then we go to the spectral requirements. As said in the beginning, CryoRad is this wide-band continuous radiometer. That means that we will be measuring outside of the protected areas as well. That means that our signal can be contaminated by non-natural emissions. And if it's contaminated, the data become useless. So therefore, we need to do very good filtering. And what you see on this figure is based on one of our observational campaigns, is the amount of data we lose depending on the spectral bandwidth we decide. And so you basically see that if we sample with a coarse spectral resolution, we have a high data loss. If we put our limit, for example, here at the 1 megahertz requirement, we only lose a very small fraction of our data. And so our spectral resolution is really driven by the noise, the potential noise in our data, not necessarily by the geophysical variables. So here again, we see how we go from observation to measurement requirements. We want this frequency range. We operate outside of this protected area. That means that, of course, we need the same frequency range, but we need this very high spectral resolution to filter out the noise. We don't need the same spectral resolution to derive our geophysical variables, because actually these are not that sensitive to individual changes. The change is not very fast over spectral regions. I've mentioned the individual observation requirements, so both for temperature, for sea ice thickness, and salinity, explaining you that they really come from these scientific uncertainties. Now, these translate in what we need on orbit. Based on our phase 0 study, we concluded then we need a radiometric resolution below NEDT, below 0.2 Kelvin, and we need stability both over one orbit and over the lifetime, being below 0.2 and below 0.15 Kelvin. And with that, I kind of like to wrap up again. You've seen these figures before, and basically what they've shown you is that we have large uncertainties in our models. We have these large uncertainties in this growing sea ice. We have these large uncertainties of the salinity in these cold oceans. And to resolve these uncertainties, we need these observation requirements. And from these observation requirements, of course, we need measurement requirements, which I also explained before, and which Fred from the ESA team will now delve into deeper on how we make it possible with CryoRad. Thank you very much.
All right, thank you, Steph, for now. So how do these requirements translate into a technical concept? Let's get started. So there is hopefully more slides. Yes, indeed. Okay, so what are the key driving requirements which in the end influenced our technical design? The first one is the spectral range and resolution. The second one is the radiometric sensitivity and stability. The third one, the spatial resolution. And lastly, our geometry and coverage requirements. On the next slide, we have another closer look at the spectral range. The spectral range, as already mentioned by Steph, is continuous from 0.4 to 2 gigahertz. And if you would express it in wavelength, coming more from the optical domain, you go from 75 centimeters down to a 15 centimeter wavelength. If you compare it to SMOS and SIMMER, these are observing at only around 1.4 gigahertz. If we then, during the study, assess this is a very continuous range, we perform some trade-offs on antenna technologies, how to cover this range. We had to split the band into 3 parts to achieve the required efficiencies: the lower, the middle, and the upper frequency. Coming to the next requirements is the radiometric performance, or expressed differently, radiometric sensitivity. This is a measure in what is the smallest change in brightness temperature our instrument will be able to resolve. And the sensitivity is directly linked to the integration time, so the available time we have above a certain point on Earth. During phase 0, we performed a trade-off between different observation concepts, including looking at rotation concepts which are, such as SIMMER. However, at the end, looking at the sensitivity requirement, which maximizes our integration time, the push-broom concept was chosen. The next requirement, to repeat again, is 50 kilometers at 0.4 gigahertz. In this scales with frequency to 15 kilometers at 1.4 gigahertz and 10 kilometers at 2 gigahertz. We can now put again a comparison to the existing mission. So this is an improvement by a factor of 2 in comparison to SMOS and a factor of 4 in comparison to SIMMER. The technical impact of this is that it impacts our orbit height and our reflector diameter. And this means, if we assume we have the spatial resolution is fixed, coming from the science, we treat our orbit altitude as a variable, and we consider the limitations from European technologies. We can perform an optimization, which resulted in a reflector size between 9 and 9.5 meters, with an orbit altitude between 500 and 530 kilometers. And speaking of orbit, we now have a closer look at our geometry and coverage requirements. So as already discussed previously, our core area of interest for CryoRad is going from 50 degrees north-south going to the poles, which is indicated for the southern hemisphere on the right. If we consider we have a push-broom observation, which in the end will limit the amount of swath due to a physical constraints we have within the fairing, this results that we need to select a polar orbit. And with polar, I mean really an orbit which goes up to an inclination of 90 degrees, which you can see also now that the satellite is flying in the animation, which gives us a dense sampling of the polar region, which will cover the pole without having a gap. However, this choice leads us that we have a solar beta angle excursion, so that means the movement of the sun in relation to the orbital plane from minus 90 degrees to 90 degrees across 1 year. And this has an impact on the satellite design, as this will need to cope with it. However, it also allows us to fly inertially stable towards the galaxy, which allows us access to calm regions of the galaxy for our cold sky calibrations. Now, okay, we need to cover it in 10 days, this region. So we can say approximately we need a swath of around 150 kilometers. If we consider we have 50 kilometer footprints, we can say, okay, well, let's just put 3 of these footprints next to each other. However, as I said before, it scales with frequency, and also we would like to have some overlap. which would result in something like this. However, also this cannot be physically fitted, as we can't put some antennas on top of each other. So we needed to stagger the antenna feeds in a so-called W shape. And now that we have a push-broom instrument, by the natural motion of the satellite along the orbit, we generate the overlap and achieve the requirements. If you now put everything together, the orbit, the coverage, the frequencies, we can generate a composite field of view which will combine all the different frequencies to achieve the required observation. And these requirements we gave to our industrial partners who developed two concepts. The first concept, concept A, was developed with Thales Italy as a prime, with Airbus Defence and Space Spain for the payload. And concept B was developed by OHB System as a prime, with OHB Italy as a payload. Each of them were supported by their respective subcontractors. We've performed risk retirement activities, for which later my colleague will give you the highlights. And lastly, we started the development of the CryoRad end-to-end performance simulator, which is led by RDA. So how does that then look in terms of satellites? We will put them here. So you can see on concept A, on concept B, they are both building on the heritage of the platform coming from Simmer and CO2M. However, both satellites needed dedicated implementations for both structure and thermal, and this is related to the change in solar angle, which needed very specific adaptation to be able to cope with that. And we needed structure to mount a large feed array and also the reflector. And finally, we also needed the changes to the propulsion to be able to fly with such a large reflector at a low altitude of around 500 kilometers. We can also look at that in terms of a mass budget. I think here the key figures to look at is that the margin to the Vega C launcher is between 240 and 270 kilograms. We fit within the Vega C fairing, with the feed array being maximized to take use of the available fairing envelope. In terms of lifetime, we can confirm that both concepts are compatible with an extended lifetime of 10.5 years, and both satellites will perform a controlled re-entry. And with that, I invite my colleague Valerie to give you much more details on the instrument. Thank you very much.
Thank you. So I will introduce the instrument itself. So both consortia follow the same functional architecture. So I will present one and highlight the main differences as we go along. So the first key element is the large deployable reflector. So to achieve a 50-kilometer resolution at 400 megahertz, we need a very large aperture of about 9 to 9.5 meters. So a fixed antenna at this size would not fit in a launcher. So therefore, we use a deployable reflector. So the reflector, it uses a lightweight metallic mesh supported by a deployable ring and a deployable boom. And its role is to collect the natural emission from the Earth over this very large aperture and focuses it to the feed array. And this type of reflector has a very good heritage for missions such as Simmer. So at the feed array, the full receive 1.6 gigahertz spectrum is divided into 3 frequency subbands as indicated by the color coding. So why this split? Well, simply because a single feed could not illuminate efficiently our large reflector across the full bandwidth with good beam characteristic. So each subband therefore use a dedicated feed that has been optimized for its frequency range. So each footprint on the ground corresponds to one feed. So the 30 feeds therefore projects 30 ground footprints. So the feeds are physically arranged in the feed array to overlap between adjacent footprints, providing continuous swath coverage. So modified helical feeds were selected by both consortia because they combined wide bandwidth, good directivity, they have a natural circular polarization and relatively compact geometry. So the feed array itself, it was developed through an iterative design process to maximize the launcher fairing occupation while optimizing the RF performance. And just silhouette is scaled to my height for size comparison. So the orange feed is about this tall and about 40 centimeters in diameter. So now each feed is connected to its own RF chain front end. So the receiver itself, it must handle a challenging situation. So it has to preserve a very weak thermal emission from the Earth while remaining robust to unwanted signal that can be many order of magnitude stronger. So the design is therefore driven by radiometric sensitivity and robustness to unwanted power signals. So total power radiometer architecture provides both with a relatively simple implementation. Now we will follow the signal through the receiver. So the first component is the input limiter, and its role is just to protect the rest of the receiver against strong signal that could damage or saturate it. Immediately after the limiter, we have the internal calibration subsystem that switches between the Earth scene and the hot and cold internal references to provide continuous monitoring of the receiver gain and offset. The references are generated using a wideband active call load and a wideband noise source. So the signal is then amplified by a low noise amplifier to boost the very weak thermal signal while adding as little noise as possible. So the receiver gain also is carefully distributed along the chain to bring the signal to the digital backend in its operating range while maintaining good linearity when we have the presence of unwanted signals. So the next block is the feed selection switch. So we've seen that the instrument contains about 30 feeds, and dedicating a full receiver chain per feed would really increase the instrument complexity. So instead, multiple feeds share one RF backend through time multiplexing. So each feed is sequentially switched to the RF backend. Each feed must have sufficient integration time to meet the radiometric sensitivity, but also be revisited often enough to maintain the required 30% overlap along track. So the two consortium use the same architecture, but optimize differently the number of shared feeds and the integration time. The signal then enters the RF backend. So although the spectrum we've seen, it has been already split at the feed level in 3 subbands. Each spans several hundred megahertz and may contain unwanted signals, which have just been amplified by our RF front end. So by further dividing each subband into narrower channel, the interference is confined to a limited part of the spectrum instead of affecting the full bandwidth. So within each subband, the signal is amplified while the limiter prevents saturation in the digital backend. And again, this subbanding has been implemented by both consortium, but with a different optimization. Finally, the subbands are recombined and sent to the digital backend. There, we start by digitizing the signal. So the plot that we see here comes actually from the airborne campaign. So the purple thermal floor represents the useful radiometric signal, while the colored peak correspond to the unwanted contributor. Now, because the raw data volume is too large to downlink, part of the processing of the signal must be performed on board. So to enable this, the signal is organized in a very fine time frequency grid. This provides the resolution which is needed to analyze the data before onboard integration. And this is really a key feature of the CryoRad architecture. So each time frequency sample is analyzed to identify eventual contamination using time domain, frequency domain, and statistical test. These algorithms, they have very strong heritage from previous mission and campaign. They will be the baseline for SIMR. And also, they have been validated by Consortium A using some synthetic signals. So the contaminated samples are flagged, and the flags are then used to be blanked. And we keep track of where they occur in the time frequency grid. Then As we've seen, because of the data rate constraint, the samples are integrated on board into radiometric pixel at 1 megahertz by less than 10 milliseconds. And this is the size of the level 1B pixel, so very high resolution. Both pixel types are then sent to the ground together with the flag information. So the filter pixels can be used as this, when the flag data can be used to understand the impact of unwanted contribution and support further refinement of the detection algorithm. On ground, then there will be some further processing, but in addition, during phase 0, Consortium A has developed and trained AI-based algorithm to further reduce the residual contribution of contamination and improve overall the data quality with very, very nice results. So the final level 1C product is then generated by aggregating all the pixels into 100 megahertz bandwidth and the full integration time. And this is the level 1C science dataset. Finally, I'll give you a brief update on the instrument technology, heritage, and risk retirement activities. I will just highlight a few examples. So at antenna level, the large deployable reflector has a strong heritage from CIMR and previous development. The mesh has been characterized by Consortium B in phase 0 at the CryoRad L-band frequency. For the feed, again, we have very strong heritage, and notably Consortium B, during phase 0, has designed, manufactured, and tested a representative feed. For the receiver, we have two key pre-developments, a wideband internal calibration subsystem and a wideband robust low-noise amplifier. And finally, the digital backend builds on existing processing units. And on the right, as already mentioned, so Consortium A has tested the algorithm and also trained AI-based algorithm for future ground processing. So to conclude, no technologies showstopper have been identified. And I will now hand over to my colleague Katja, who will present the performance achieved with both consortia. Thank you.
Okay, so I will go through the level 1B compliance summary, starting with the geometric performance. So both concepts, they have delivered designs that are compliant within our coverage, our observed area, as well as they meet the 10 days maximum revisit time. In terms of spatial resolution, as it was already mentioned, this is directly dependent on the reflector size. And because of that, we have maximized the reflector size to fit the launch envelope to get the best possible ground footprint. So both consortia, both concepts, they are overall compliant within specified frequencies, with a minor non-compliance for concept B at 0.4 gigahertz. But to mention that they start being compliant from 0.43 gigahertz onwards. So therefore, this is deemed as a non-critical optimization point for phase A. Then we look into the overlap between neighboring footprints. So the along-track overlap is met by optimizing the revisit time of each feed as the satellite moves forward. And both concepts are compliant for the 30% along-track overlap within CryoRad's bandwidth. As said by Valérie before, so each footprint on ground corresponds to one physical feed antenna. Therefore, the cross-track overlap is achieved by optimizing the feed positions in the focal plane. So for frequencies over 1.4 gigahertz, both concepts are compliant. Below this frequency, compliance is high, with concept A at 91% bandwidth compliance and 98% for concept B. And it's important to mention that this exercise of feed placement optimization is still ongoing by both consortia, and it's expected that full compliance is going to be met by phase A. Next, we go through the radiometric performance. So to meet the radiometric sensitivity, there has been some optimization through the push broom integration time while keeping low system noise, good receiver calibration gain, and receiver stability, and calibration performance. So both concepts are compliant. Then we talk about the radiometric stability, which describes the long-term consistency of the calibrated brightness temperatures. Over one orbit, the main challenge are the thermal changes that can occur within this time scale, such as during sunlit or eclipse conditions. Whereas over lifetime, other contributors may become more impactful, such as the instrument aging or long-term calibration drifts. So both concepts are overall compliant, with a small non-compliant compliance for concept B with regards to full mission lifetime. And this is directly linked to conservative performance assumptions rather than a limitation on the calibration approach. So the radiometric performances that I have just presented is supported by a calibration strategy for CryoRad. And this is divided in 3 layers. First, on-ground RF characterization of the integrated radiometer, as well as the antenna characterization. This is to assess the pre-launch calibration knowledge, as well as the residual pre-launch errors to be used in the performance budget. Then we have in-orbit internal calibration that uses internal references, such as hot and cold loads, so that any instrument gain and offset drifts are tracked. And finally, external calibration and vicarious calibration, which relies on stable references such as cold sky view or thermally stable places on Earth in order to monitor these long-term drifts. And all of this is supported by SMOS and by then Simmer Heritage. So the CryoRad end-to-end performance simulator at this phase is well advanced, with many of the modules already implemented. And just to illustrate here an example of a simulated level 1B product of sheet temperature. So we can see here for the 3 frequency ranges, some spatial variability that depends with the frequency. So full end-to-end capability is expected for phase A. And to conclude, the phase 0 assessment has confirmed a clear technical path with no mission-level showstoppers identified. We have presented 2 technical concepts with optimized mission architecture that delivers the key performance requirements. And most importantly, CryoRad enables a unique observation capability with continuous low-frequency, wideband measurements of polar regions, which will open new opportunities for cryosphere science, which my colleague Laurent will further explain. Thank you very much.
Thank you, Katia. So I will go back to research, science presentation. I'm Laurent Bertineau. I'm heading the Copernicus Marine Services Arctic Forecasting Center. And I will come back to the radiative transfer concept with the brightest temperatures from CryoRad, measuring emissivity times temperature, and the 3 media we want to observe. So we have ice sheets, which are for which the temperature is critical, sea ice and ocean water, for which the emissivity is critical. And the emissivity is a function of the natural material absorption as well as its structure. I will take the 3 media in the order. This is the ice sheet. We know it's cold at the surface, warmer at the bottom. The absorption, as a consequence, is weak at the surface, strong at the bottom. You multiply both, you obtain a very strong emission in the bottom and low emission at the top. So that local emission, we want it to reach the surface. And for that, it has to be transmitted. And in high frequencies, CryoRad may mainly see the cold top only, but if you move to low frequencies, then you can see the warm bottom. This schematics is translated at phase 0 calculations. in the ice sheet profiles from west to east of Antarctica at crossing the deepest. So you have an ice sheet that can be 3,000 meters depth, 3 kilometers. That's the distance from here to the icebreaker we had yesterday evening. And you see temperatures of minus 50 degrees at the surface, warm, around zero, melting or not at the bottom. And you see that the red colors in the bottom, that's the sensitivity. So there's a convolution of the temperatures across depth. And you have seen now that when you go below 1 gigahertz, then the sensitivity moves down to the bottom of the ice shelf. And that's what gives us hope that this is going to work. Now we extrapolate that to the whole Antarctic ice shelf with the temperature uncertainty related to a radiometric uncertainty of 0.2 Kelvin. How does that translate compared to a requirement of 1.5 Kelvin? And with the well-accepted Metzler absorption scenario, we see that we are valid on 95% of the bottom area. This is very comfortable within the requirements. Now, as a sensitivity test, you can triple the absorption and still have 65% of the Antarctic bottom within the required 1.5 Kelvin. So, phase 0 was the opportunity to go into this terra incognita of what is the absorption and the P-band, never observed before. So we've had this very interesting resonator, golden-plated, safely stored in Switzerland, in which you can put ice samples of different sizes. So in this equipment, which is very precise, you can actually revise the Metzler absorption scenario in the P-band. And so initially, with laboratory ice, you obtain a curve of how much is the absorption as a function of temperature, of course. And we see that Metzler actually is a correct representation according to the new measurements. And this has been done in phase 0. We will need more and more realistic ice samples to be put in a resonating chamber to have our hearts clear on what we can expect. Then I move now to sea ice thickness, where the absorption is much stronger because of these salt brine inclusions into the sea ice. Also, the sea ice is over seawater, which is very absorptive. And this means that we want we're not looking at kilometers of penetration now, we're looking at a meter, or hopefully a little more. And for that, we know the heritage SMOS showed us the way, because SMOS gave us this unexpected third child after soil moisture and ocean salinity of having sea ice thickness for thin ice. The graph you have now see to the right is the sensitivity of brightness temperature to sea ice thickness, and the different lines are different thicknesses of sea ice. So the thinnest ice is the top line, the red line, and you see that at 1.4 gigahertz, which was the SMOS frequency, there is a sensitivity. You see now that into the P-band, all the way to the left, this sensitivity is multiplied by a factor of 5. So there we can have good hopes that this will be a much more interesting measurement. Now, at 0.4 gigahertz, same, you see the other lines of thicker and thicker ice raising up. See, the 0.8 meter is at the same level of sensitivity as you had at 0.4 meter for the 1.4 gigahertz. So now, the first sea ice grows from nothing into 1 meter within 1 year. And now we see that we can have a continuous observation of this growth of sea ice throughout the season. So the brightest temperature is sensitive to ice thickness, but not only sea ice thickness. There are sensitivities to other parameters that we also wanted to look at. We took here in phase 0 a situation in the Southern Ocean with, on the climatology of sea ice. And what we see is that the sea ice concentration is also visible in the P-band. It's visible in all the frequencies, so that's no surprise. And in a way, it's actually comforting to see that, because then the sea ice thickness is, as I've seen, also more sensitive in the P-band. we can also look at other more, say, exotic parameters of the sea ice. And this one, for example, the sea ice salinity, you see this interesting crossing line in the low frequencies, which says that, well, there is, say, a scope for evaluating more sea ice salinity in the future. Now, note that this curve here has been amplified by a scale of 10 times, because, of course, the sea ice salinity is much less important than the sea ice thickness and concentration. Now, having other parameters also in the picture, you see that there's mostly sea ice concentration thickness as important parameters. They can be retrieved because the curves are, say, going up and down at different frequencies. We have, maybe you don't see very much the color shading, but there's 1600 bands observed by CryoRad. So it is a good place to start disambiguation and inversion of the most important parameters. I'm now moving further to ocean water, sea surface salinity, with the important effect of salinity on the brightness temperature. You see now, similarly, as a function of frequencies, how sensitive is brightness temperature to sea surface salinity. And the different curves this time are waters of different temperatures. The top line, the red line, is 30 degrees, tropical waters. This is, say, this is observed by SMOS in tropical waters, and it is, has a high sensitivity. If you follow the red line into the P band, there's no big change here, same sensitivity. Now you move to cold waters, 0 degree, and then, indeed, the sensitivity to salinity is degraded quite a lot in 1.4 gigahertz. It remains exactly at the same height in the P band, very sensitive, or sensitive. Now it's a factor of 3 compared to the L band. The sensitivity to surface salinity is also important. I want to measure this, that the Arctic waters can be as low as 15 PSS, gram per kilogram, and that actually makes the mission shine, because you see this crossing of lines, and you see that the P band is 6 times more sensitive to the salinity in fresher water than it is in the L band. Now, further, there's dependencies on ocean temperature and wind speeds that we have to take into account. And this has been taken into account in this phase 0 study, in which you see how an anomaly of surface salinity, similarly to the anomaly of thickness before, translates into a signal-to-noise ratio at different frequencies. And we want here to have a lot of red in these pictures, because red is our happy place, is where the signal beats the noise. And you see that for the Arctic salinity, there's a lot of red from the Chukchi Sea, the Siberian shelves, that are otherwise less, that have more noise in the L band. And in the Southern Ocean, you can also see the same areas shown earlier with the anomalies of salinity, less strong anomalies, but still some signal-to-noise ratio in the red, in the L band, in the P band, sorry. So the L band needs about 1 PSS of anomaly to beat the noise, whereas the P band only needs 0.3 PSS anomalies to have a signal. Now, as my summary is the same as you've seen before, we have these problems of having uncertainties in the world we see today. In the future, the world will be different, and if, with the help of CryoRad, we can have, with these sensitivities to our signals, to our variables of interest, this is a good place. We think it is realistic to have the requirements met at a precision of 1.2 Kelvin and stability of also below 0.2 Kelvin. And that being said, I would like to introduce Giovanni Macelloni, who will give us the final words.
Thanks, Laurent. I'm Giovanni Macelloni from National Council of Research, Italy. So Laurent demonstrated to you that during phase 8, we did a lot of theoretical study. We developed model, we know radiative transfer, but I'm happy to inform you that we also proved that everything that we saw, it's already proved. So most of the things stems from the SMOS result, L band, And for instance, here I represent what we did with the ice sheet temperature. We demonstrated that using SMOS, it's possible to retrieve ice sheet temperature. This is in the top figure, of the two different depths. But as you can see in the bottom figure, when we go deeper in the ice, we approach the bed, the uncertainty is high, because as explained by Steph, the penetration depth is not so high. So we are not able to reach the bottom. But the concept is feasible. We develop a methodology. We develop a retrieval, so it's good for us. So the message is we cannot reach the basal temperature, which is the key information that Anne present us. But in between, thanks to our US colleagues, we developed a collaborative project, and NASA put money to develop a CryoRad-like airborne demonstrator, and we flew in Greenland and in Antarctica for testing the technology and testing the ideas. And you can see here we have a flight over center of Greenland where there are some boreal for testing our retrieval. And in the figure below, you can see here that we are able to retrieve temperature. The figure represents the temperature profile from the top to the bottom in the same flight lines. And you can see that we are able, this is an interpolation, we are able to retrieve the temperature. We prove that we are able to retrieve the temperature. And the other important point that we mentioned, we are specifically interested to the basal temperature, which is the figure on the right here. And you can see the black line represents what given by airborne instrument, while the black dot represent measurement in the boreholes. So you can see that points are sparse. These are 20 degrees of latitude, but using a continuous information, we can follow completely the dynamics of the basal temperature along the ice sheet, and then provide information that are relevant for understanding if the base is wet or not, or other information about viscosity and sliding of the ice sheet. Same story for the ice sheet as already, for the sea ice, as presented by our colleagues. SMOS already provide information on sea ice. We know that there is a good cryosat and SMOS combination to have reliable information on sea ice. But as shown by Laurent and another by Steph, there is a problem when ice is above 50 centimeters with SMOS because of the penetration depth of SMOS. So also here, our American colleagues fly in Greenland, in the northern part of Greenland. They catch some sea ice spots. And on the top figure, we have in colors different channels, CryoRad-like, that show us the sensitivity to the different frequency to the presence of the ice, that allow us to discriminate thin and thick ice. And you can see also the dynamics that the multi-frequency can provide us. And having this information in our hand, we are able to retrieve information on the sea ice thickness. Last, on the sea surface salinity. You know, everybody know that SMOS was a game changer for oceanographers because they provide for the first time sea surface salinity from space. That was known just on the Argo buoys before. So it's a really game changer. SMOS and L-band works quite well. Here we represent a result of a monthly salinity retrieved by SMOS compared with Mercator reanalysis on the same place on the Southern Ocean. Here is Antarctica below. And you can see that SMOS works quite well. It's able to retrieve quite well. But there are still high uncertainty even on monthly maps in the cold water. At the moment, we don't have data with a CryoRad-like system, but we did some synthetic analysis. Here, it's again a reanalysis using GLORIS on over one day, just one single day, in the same area on the Southern Ocean. And you can see the dynamic that we can catch of salinity on this day. And if we use SMOS for single day, this is the result that we can imagine. So we are not able to find the differences in the salinity in those areas. If we use CryoRad-like system, we are very much better to represent what is the real situation. So that's confirmed that our ideas are not completely crazy, but we can do it. We have data. So I tell you about the US friends that developed this instrument, but I'm happy to inform you that also in Europe there is an effort for having the same story. So thanks to the Italian Space Agency, we developed the instrument, and then thanks to ESA during phase 0 study, we certified the instrument so it can fly. This is the proof that we have the certification, we have the stamps. It's not trivial. It's not a trivial game. So we have it, and then we perform a first attempt to demonstrate that the instrument can work. It could be very useful for next phases, obviously. We try to collect multiple data. So we flew in the Baffin Island, northern Canada, close to Greenland, and also we go to Greenland. And the aim of the campaign was exactly to collect the data on the sea, because I demonstrate you that we don't have data on the sea at the moment. So we have a 60 hour of flight, so we collect a lot of data. This explains how this 1 megahertz imply in terms of data. And the good things that we coordinate our effort with the Canadian expedition, Amundsen expedition. They collect salinity over our flight line, so we can compare our data with the real in situ data. The calibration is undergoing, so unfortunately I cannot show you brightness temperature data at the moment, but what I can show you, it's a result that already presented by other friends. It's the frequency, this is the frequency, this is the time, so it represents some grid line here. And you can see here some interferences that we also discussed above. And you can see that some bands are affected by interference and some not. But in total, the good things at the maximum, the impact was also in this very contaminated area was less than 20%. So we save the information in any case, having such huge number of bands. I want to talk about you a little bit more about a non-natural emission. What non-natural emission means? It means broadcasting, television, telecommunication system that we know affect our signal. It's clear. It's not a problem that affects just CryoRad. Nowadays, it's a problem for all the microwave emission, and there is a lot of effort for mitigating this effect. Active and passive doesn't matter. And radio astronomy also developed this methodology for a long time, because also they are affected by similar problem. So CryoRad is perfectly the testing mission, because it works in hyperspectral mode with this very fine resolution of 1 megahertz, and we work in areas where we expect that the number of transmission is low, because we go to the poles. And especially, you can imagine in Antarctica, the number of people is very limited, so also the anthropic contamination is very low. And this figure represents a cumulative histogram of number. The blue line is the density of transmitter, which is obtained by the database of ITU transmitter. And as you can see that as we can move from the pole, from the 45 degrees of latitude to the pole, the number decreases. So we are confident that this tend to decrease. But it's also important that we are also identify the sources of the non-natural emission. We know which kind of sources we can encounter in our emission, and for each sources we have strategy to detect and then mitigate this effect. So I don't want to enter in the one by one list, but just to say that for each of them we already have a strategy to handle. And as demonstrated, as shown before by my colleagues, we already tested in this Canadian campaign with the airborne, our capabilities. And here I show you an example of one acquisition. This is time, this is a second, and these are frequency. This is in the first part of the band, 400 megahertz, 800, and this is in the remaining part. As you can see, here's power, so it doesn't matter of the shape, is the power as it is at the antenna level. So you can see here there are some frequencies where we have this big spot, and you can see here the scale of the power here and here, and applying those algorithms that also Valerie describes before, which can be used also in our satellite system, we are able to remove most of these things, and you can see the scale change. This is completely changed the scale, and you can see that we have a more normal shape, and then from this shape we can easily recover the brightness temperature in a proper way. So talking about how the system works, I want to spend some few words in illustrating how we move from the level 0 data that we acquire by our antenna to the products. So a little bit the processing chain of our data. So some detail are already provided by technical colleagues, but I just want to provide you a very quick overview. So we start from level 0, so row counts. Then we have this 1 megahertz data for mitigate and to detect non-natural emission. And then after that, we try to combine the data to have a better sensitivity, because as much wide is the band, as much the sensitivity is better. So, and we reach to the level 1C. Then from level 1C, and using the retrieval algorithm, we are able to move to level 2, which use also ancillary information for better characterization on our parameter. And we are able to deliver the sea surface salinity and sea ice thickness at level 2. And then we move to aggregate the data. And it's important to mention that for the ice sheet, we move to the level 3 because we need a lot of data to be sure of the quality of those data, because the sensitivity is very small, so we aggregate the data. But in this case, you have to think that ice sheet is very stable in 6 months. If it's not stable in 6 months, we are in trouble in any case. So this is not a problem of CryoRad. So we can use the high accumulation of data to improve the quality of our brightness temperature and retrieve with a better sensitivity the temperature profile of the ice sheet. And then finally, we can also aggregate data and play a little bit around to have level 4 data to be distributed to the wide community. So this is it for the primary objective, but as reminded by other friends, we have a global mission. We not stop at the pole. We look all over the globes. So, and we know that using these low frequencies, we are able to catch other information in other domains. And the most popular are what already done by SMOS, soil moisture, but also soil freeze and thaw, but also vegetation. These figures demonstrate, again, how the benefit of the different frequency is, because we penetrate in a different level of soil or vegetation, and using that we can infer information on this quantity. So finally, I want to move to the complementarity and synergy with other missions, because we know that we cannot work alone. We do some work, but we don't work alone. So here I just emphasize which are the European mission that we'll have in the microwave domain at the time of the CryoRad launch. So there is a many possibility to collaborate and cooperate with other missions, but as said by other colleagues, this is unprecedented large band which is not touched by the other system, so we can benefit of that. So using all this information, and as Anna, I want to return to one nice slide that Anna presented at the beginning. We plan with our product, with our PMO product, to contribute to solve some of those questions that I repeat largely here. And just to summarize, we find the table also in the report. Obviously, we cannot solve a question, an ESA strategy question with one single sensor, but we know that adding our frequency there, we can contribute to a new insight of this problem. And for instance, I can highlight here that this information can be provided just by our system, no other way for the ice sheet, and then for contributing to this question. And for sea ice, again, we are the benefit of providing information for sea ice thickness for growing ice and also other parameters, which together with other sensors can contribute to solving this science question from the ESA strategy. And finally, for sea surface salinity, I highlight again that our big benefit is solving the question in the cold water, which is not solved nowadays by current mission. So this concludes my talk, but before concluding, I just would like to remind you, which is the great novelty of this mission, which is perfectly in the spirit of the Earth Explorer, is a new band, new technology for new parameters that we plan to explore. So the main parameter is this one, which is completely new, but thanks to the capability of the hyperspectral radiometer in this PL band, we are able to provide information on other essential climate variable, sea ice thickness and ocean salinity, and many other also, as I explained. So thanks for your attention.
So thank you, Giovanni. I picked up one thing you said about one of your goals. It's not crazy, we can do it. I think that helps for many of the Earth Explorers when you look at what has been presented over the last 2 days. It's really crazy, and I'm confident that the scientific and the technical teams, that they can really do it. Again, as for the other three, now here number 4 presentations. Also here CryoRad was just presenting an excellent results. You can again see, and I actually like repeating myself in that case, that you can see the hard work that has been going into this over the past 2 years. Again, thanks especially to the presenters. It's not easy to stand up here and to present on time, and you were very much on time. But also, of course, the MAG, the technical teams in ESA, science teams in ESA, the campaigns, industry as well. So again, thank you so much for the last 2 years, and in particular also for giving us this excellent presentation over the last 1.5 hours or so. Thank you so much. So we're coming again to the more housekeeping part, and again I will be quick, as Bernardo has the more interesting technical parts then to cover. So on the scientific maturity, as said before, this is again our way to ensure that the programmatics on the science side are fulfilled. And also here, considering the CryoRad Phase 0 science preparatory activities as documented in the report, and again, the report has been an excellent one, and again I invite you to read the report and all the other reports as well. Then also, of course, of today's presentations, the MAG and the campaign study teams, they have really shown that on the basis what they have done, we can really judge that the candidate mission has demonstrated to be of scientific mission concept feasibility, what we require to be as an SRL4. So again, excellent work by the teams to have demonstrated this, and also as part, obviously, of the presentations. So the second part is then on the risks, and also here, with respect to the identified scientific critical areas and risks, the CryoRad MAG and the campaigns, the study teams, they consider that overall this carries a low scientific risk, the mission. So of course there are still things to do, nothing is perfect. So should the mission be selected, there's also a credible scientific roadmap that has been identified. to further mature the science towards a higher scientific readiness level, towards scientific level 5, which includes in particular the refinement of the end-to-end simulator here, which includes the adaptation of the scene generators, scene generator in particular with respect to background contributions to radiation. Then, of course, the processing from level 1B to level 1C, the prototype of the level 2 retrieval algorithms, so making use of this full spectral resolution and bandwidth that CryoRad will be providing us. And then, of course, on the performance model and the actual test metrics to ensure that this can also be all demonstrated, the performances can be demonstrated. And then, of course, we had seen that there is a lot of campaign activities ongoing, and they would be continuing with airborne and ground-based campaigns over, of course, one of the key areas, Eastern Antarctic Plateau, to validate the retrieval models. And then we've seen this wonderful laboratory pot, I'm not sure how to call this, that will also help us to fundamentally understand the dielectric properties of ice. And with this, I hand over to Bernardo. Thank you.
You forgot that. Okay, thank you, Torsten.
No, it's fine. Okay. You can proceed into phase 8. Sorry.
Thank you, Torsten. Good afternoon, everybody. And it is my privilege to give the last presentation of this UCM and guide you through the technical part of the programmatics for CryoRad, providing you, as with the other mission, with an overview of some outcomes of the phase 0. As you see, I'm going to do the talk with low frequency only. So during the phase 0 preparatory activities, each consortium has defined a system concept with the capability of fulfilling CryoRad mission objectives and requirements, as you've seen in the technical presentation. It has also identified the main technical risks that I will show you later. And also, after this, it has also been identified risk retirement activities for which they have also put in place. I've used in some of them in the as well technical part. And a pre-development plan has been also put through in order to make sure that at the end of the phase V1, there will be a TRL 5 on critical elements. In terms of heritage, critical areas and risk, and once more for maybe the people that are only on this session, when we are referring to critical areas, we are not only referring to items that might have low TRL, but also other elements that are crucial for the mission performance and for which we need to pay attention and focus during the phase A. At satellite system level, both consortia have proposed concepts which are based on ongoing Copernicus system expansion developments, particularly for CMAR for Consortium A and CO2M for Consortium B. In both cases, this platform requires a custom structural design to accommodate the antenna, and also other adaptations in the thermal control and electrical power subsystem, just to take into account that we will be flying in a non-synchronous orbit. Both consortia plan to reuse the avionics of the Sentinel expansion missions with minimum adaptations. As also with the other missions, none of these adaptations at platform level are considered to introduce any significant technical risk at this stage. CryoRad is compatible with Vega C launch mass capability, and it is about around 10% more or less for both consortia margin. That will allow design evolutions or potential design evolutions in terms of mass. However, as you've seen, CryoRad uses all the Vega C available envelope, and therefore this is a point in terms of accommodation and volume that it will be a focus during the phase A. Regarding non-natural emission detection and mitigation algorithms has been extensively discussed during the technical and also during the scientific part. But as a conclusion, as it has already been shown, the phase 0 has reviewed and confirmed the capability for successful detection and flagging of these emissions, and also the capability of emerging AI techniques to mitigate this impact. Therefore, the phase 0 has concluded that the non-natural emission environment is manageable and it can be handled by the CryoRad concept. Nevertheless, given the importance, it will be also focused during the phase A. At payload level, there are 3 items that have been identified as critical. The Large Deployable Reflector subsystem, although it is important to mention that it is derived with a large heritage from the CIMA reflector development, and that there will also be some adaptations, as already mentioned, on the mesh, boom segment mechanisms and control electronic, because the size is different from CIMA. In terms of the feed arrays, there is a long-lasting heritage on helix-based radiators. However, on some frequencies, the manufacturing approaches had less heritage, and this is why risk retirement activities were already initiated and already breadboards were produced. Another element that needs to be paid attention is the mutual coupling between the feeds, because it affects the configuration and the spacing, that it is also coupled to the spacecraft accommodation of all the feeds, and also with the launch fairing constraints. As also mentioned during the technical part, the optimization of this array will be a focus also in the phase A. Finally, a RF receiving subsystem and calibration concept. It is driven by the wideband operation, the large relative bandwidth, and the matching constraints. Nevertheless, there are already ESA developments ongoing on the calibration concepts based on active call loads and P-band, and also on the LNA's performance. Based on these critical areas, as with all the other missions, a pre-development plan to increase the TRL to 5 at the end of phase 1 has been put in place in these 3 areas, but particularly in the feed array and the large deployable reflector subsystem. Feed array, there will be breadboards and engineering model to mature the individual feeds and also the complete feed array. So continue with the activities that has been already initiated. In the large deployable reflector, the first thing that it will be done if the mission goes to phase A is to assess the applicability of the CIMA EQM approach, so that the model philosophy can be simplified. And also maturing all the other elements that I mentioned before in terms of mechanisms, tubes, and the mesh. Regarding the RF receiving and calibration subsystem, continuing with breadboard and EM, so this a little bit on lower priority on the call loads and also on the LNAs. In general, the phase A technology pre-development plan that has been put through for CryoRad is considered suitable to increase the TRL up to 5 at the end of phase 1 and retard the identified risks. In terms of development approach, CryoRad, as same as all the other 3 missions, will follow a phase B2 CDE1 development, and both consortia have proposed the same parallel development for the instrument, the reflector, the platform, and the satellite activities in order to optimize the schedule. Consortium B at platform and satellite has proposed a model philosophy based on a structural model and a PFM approach with flat sat for avionics and payload interface. And Consortium A, however, has proposed a direct PFM approach with no structural model, which is considered that it may introduce risk given the level of adaptations that it requires the platform, particularly in mechanical areas. Payload, the instrument will follow an EQM PFM approach, while the deployable reflector will have at this moment, and it is following a conservative approach until the suitability of the EQM of CIMA is demonstrated, it will follow a EQM PFM conservative approach. Finally, last 2 items, schedule. I guess by that time you will be figuring out that the schedule is driven by the instrument development. And also based on the phase B1 and phase B2 kickoff dates, assumed at this moment, launching the 2036-37 timeframe is considered achievable. Other programmatic considerations, the CryoRad technical baseline adheres to the relevant ICS standards applicable to the explorers. It is also compliant with the currently applicable space debris regulation. It also follows a control re-entry approach, and there are no ITU regulatory issues identified. And finally, also, although you have a spoiler during the technical part, no technical mission showstopper has been identified for CryoRad and Explorer 12 mission candidate to proceed to phase A. And with this, conclude my presentation, the technical part of the programmatics. And as with all the other missions, you can see, again, the large amount of people who has been working on all these areas, and already Dustin mentioned, but I would like also to give my gratitude to all the team, particularly starting with the MAC, all the scientists and scientific institutions participating in the science studies campaigns. As you see, a big part of the mission. End-to-end performance simulator, ESA colleagues, yourself for attending, and although I know that it's going to be also mentioned after, to all the people who has been working in order to make sure that everything here in the UCM is functioning and running perfect. And thank you. I hope you enjoy all the presentations. And now I pass the question to Cyril. Thank you very much.
So good afternoon. My name is Cyril Crevoisier. I'm from CNRS, LMD, HEO member, and so I will take over from René to host this Q&A session on CryoRad. And so I'm sure that you are all familiar with the concept now, so we have 40 minutes all together. And first, I wanted to thank also, in the name of HEO, for, again, an excellent presentation on CryoRad, and also very good document that you should all read, definitely. And so now we can start with the questions. So who wants to go first? Yeah, at the back.
Okay, Klaus Schmidt, German Space Agency. So, first of all, great congratulations to the team and the presentation, a very interesting presentation. We have seen during the 2 days, I think, fascinating presentations from all teams. And unfortunately, it's now the task for HEO to come to some prioritization. And therefore, yeah, competition is tough. Yeah. In my understanding, part of the selection is what are the most important missing, observable, and the quantitative, substantial contribution a mission can do. So you in your observable area has shown that there is and there will be a full fleet of science and operational missions dealing with a lot of parameters. So starting from CryoRad-2 over SMOS, over SMOP, microwave radiometer, Sentinel-1 and 6, operational mission Rose-L, Simmer and Crystal, all facing partly or completely the pole areas. The question leading the report, for at least for me, remains you have shown a lot that you are contributing, that you have complementarity, and you have synergy. But what is the missing observable CryoRad is addressing, and why does it matter? So you have shown that there's something missing. At least in my understanding, it was not so clear whether this is the most important parameter we need for climate action. Yeah? You have shown interesting scientific observables, but are these really the most important one? And to put it in perspective, in 2040, most of the Arctic region is mainly ice-free over the whole summer. And in the Antarctic, most recent peer-reviewed publications have stated that already severe irreversible ice thinning loss has been done. So the remaining thing you are observing is like you're looking at the glaciers when they are already disappearing. So is this mission really timely? Isn't it too late? And is the observable you are claiming for really the most important one? So this is a question I want to put forward.
Okay, I think this is addressing ice sheets, and I will, with the answer, I will give it to Steph for a first shot.
Thank you for the question, because I think it's a really important question. I think what CryoRad makes us unique is that we have this very low frequency P-band radiometer. And we will be the first one to really measure the temperature until the base of the ice sheets. We've shown a lot of complementarities. For the sea ice, for the salinity, there is definitely complementarity. We do something unique there, but we are absolutely unique in these temperature profiles. Having said that, are we too late? Ice sheets are huge. You've seen in the figures, they reach up to 4 kilometers depth. So even in a terrible climate change scenario, they will be there for centuries, even millennia. And one of the main uncertainties we have with these ice sheets is how to run the models. I think Anne has shown very clearly that we have good models, but we have a lot of difficulty. They have a large uncertainties. And one of these large uncertainties is how to initialize them in terms of temperature, because that actually determines how fast the ice flows. And with CryoRad, we will be able to answer that question or to fine-tune this model. So I think we are more timely than ever, because sea level rise is there going to be for centuries to come. Even if we would do complete climate action now and would stop now, still sea level rise is something that's a very long-term commitment. And so by being able to constrain the models and understand how we should put these physics into the models, we will be able to solve that. I hope it answered your question. Thanks.
Thank you very much for a very nice, interesting presentation. I had a question about the, so you say you show the ice profile in temperature, and could you expand a bit more what the influence is of the geothermal heat flux? Because it was also on the last slide that one output would be also on the geothermal heat flux. And this is one variable which is very, very difficult to get with other means. And maybe, so one, what you can say about heat flux, geothermal heat flux, and two, then what is the influence on the ice, basal ice temperature?
Thanks for the question. I think this is a good question for Anne, our ice sheet modeler, so she will know.
Thank you. Yes, and thank you for that question. So we will be able to retrieve the geothermal heat flux in the areas where the ice is frozen, in the areas frozen to the base, to the bedrock. In the places where you have melt, you cannot, because then the energy is going into melting at the base. So in the frozen areas, we will be able to provide estimates of geothermal heat flux. And so what is the effect of the geothermal heat flux? If you recall the figure showed by Steph with the yellow, orange, and red coverage on the in Greenland, it showed a simulation with the same model using the same setup, but with two different geothermal heat flux maps. Because several geothermal heat maps out there, they're very different, and it makes a lot of difference to your estimate at the base, where it's melting, where it's frozen, depending on your choice of geothermal heat flux maps. So that's definitely a question that's also very important for ice sheet evolution.
Again on this question before that last one, could you elaborate a little bit about what it means that you will be more precise and accurate in defining, for instance, the rate of sea rise in the coming decades or whatever? We understand this parameter is important, but could you be more precise? In particular, I don't know if you were referring to the same plot that you have shown before. There were these different calculations in different locations on the northern and the southern ice packs that are melting and heating up in different ways. You have shown that the different areas are contributing to the sea rise in different ways in one of your charts. Is that the result of the current model? Is that the result of the current model plus the benefit that CryoRad will bring in? Could you be more precise about how improved the model will be? Not just everything will be improved, of course, but more precisely, will we have an indication that the sea rise is such values as because of this new variable that we're bringing in?
We did some analysis in the science studies. We didn't show it here. And I think another question for Anne, because it was your team analyzing exactly this effect.
Yeah, I can try to answer this. So I think you're referring to the figure with the tipping points. What we will do in CryoRad is to provide temperature. And I mean, while we cannot, so this would be a contribution towards understanding this. But what we can see and what we have done in the science studies is that we have tried to investigate what happens if we perturb the temperature profile. So like, what does this uncertainty mean? So what we aim to do is to make the projections more precise. But there are also mechanisms inside the ice sheets that we don't understand that maybe CryoRad will not be able to answer. So the sudden collapse of ice shelves or ice shelf instability like this. But we can provide estimates of, okay, so within the current knowledge and current model setups, we tested with 2 different models, state-of-the-art models, so Grizzly and PISM. And we tested what happens, okay, if we perturb the temperature both or have a bias, a warm bias or a cold bias. And we could see that, for instance, if we try to reproduce using the same setup for a projection using RCP 8.5, it adds, if you have a warm bias, it will add a significant amount to the projected mass loss. So it's like between 10 and 20%. So if we can reduce this, this would be a very nice thing. What we cannot capture in this is that hopefully having this, I mean, closing this observational gap will also enhance our understanding of the processes that we are not currently including. So this is something that's very difficult to quantify, right? The things you don't understand. So hopefully it will be even more using this new data set.
Jonathan?
If I may add a related question, I think it's that really belongs to that. You showed that enormous spread in the projections, and I think you were referring to that. And I think you argued very plausibly that knowing the basal temperature will reduce that gap, that spread, right? That's sort of qualitative, right? I think it's plausible, but can you make a quantitative statement? What are the other drivers behind that spread? I would assume that it is not only this one parameter, and very likely there are very different parameterizations in the different models. So is this first order, and will it reduce the spread, I don't know, by 90%, or what is your estimate there?
I will not reduce it by 90%, I think, as you say, there are other components that we don't understand. This is one of them, and I think it's an important one. It will reduce, and we can see that, as I said, I mean, within the bias that we're going to provide, within 2 degrees, we see if we have a bias in the temperature of 2 degrees, you have faster flow, and you will have more areas with sliding within your model. So this, so it affects your estimate in the end, and the processes that you can constrain.
I think Steph wants to add something.
Yeah, I think the processes are also different for the different ice sheets. So, for example, Antarctica is a marine ice sheet, so it's also driven by ocean melting at the edges. And ice shelf stability plays a key role, because this is kind of if you have a sinkhole, it's kind of the slow car in traffic that keeps the rest of the cars slowing down. And while this is not our primary research objective, our primary research objective is really to get these temperatures. CryoRad will also be extremely useful to measure these regions that are melting at the surface, like, for example, the ice shelves. We didn't touch upon here because we wanted to really focus on this on our very unique thing. But I think CryoRad will also extend to these other uncertainties we have also in these ice shelves, ice sheet processes. But I don't think we can quantify at this point. We will go, the models will converge by 40 or 50%. I don't think, I hope we can, in phase A, further work on reducing these.
Okay, so, Jonathan Bamber, University of Bristol, TUM, Accio. Following on that, I mean, let's focus on the things that you are defining as unique here, and actually, your title is instructive. It's delving deep into ice sheets, so I presume it's the ice sheets that's the primary focus here, right? And it's ice temperature. And now I have a little exam question for Anna, I guess, which is, you know, that plot you showed, which was the ISMIP6 projections going out to 2100 or 2300, there's a big spread, some are positive, some are negative. In the list of factors that are influencing that uncertainty, that spread, what is top, what is next, and, you know, going down, and where is ice temperature, and not basal traction, but whether it's a wet or dry bed or not, because that's not the same as basal traction. Half the models in that plot are isothermal because they use the shallow ice approximation. Some of them are similar. Some of them use as initialization ice volume. Some of them use surface velocities. You know, so it's actually not entirely clear to, let's say, I mean, I'm not the ice sheet modeling community, how they would use end glacial temperatures to improve the projections in their models, because there are many parameters that are tuned. And actually what you want is ice rheology, which is not the same as end glacial temperature.
Question understood, and I think you want Anne.
Whoever feels suitably qualified for that one.
Okay, so I think there are several questions or issues within what you're asking. So one thing is that, yeah, of course, models are different and they use different approximations to the physics. But one thing that they all have to somehow get at is the viscosity of the ice. And some of them do like the two models we have used in our science studies. So then you need to know what the temperature inside the ice sheet is, and they're initialized through a glacial cycle experiment. And this is done in order to get a present day state that is, that's consistent and, to fill in this viscosity gap. And then afterwards, in some models, they run forward, assuming this, and they can have different formulations for what goes on at the base. Some models, they then, we say now we know the viscosity. We can then use other well-known, well-observed data sets of surface elevation and flow, and they can then invert and get an idea of what goes on in the base given this. Some models, they also claim to be able to at the same time invert for the viscosity in the ice column, so then it's the entire ice column. As well as the basal conditions. But all of this is just in order to get a correct initial state. And I think no matter the type of model or approach you use, knowing what the temperature inside the ice sheet is a very good start to initializing your model. And I completely agree, it's not only temperature that governs viscosity, it's also impurities and so on. But it will still really sort of constrain what you can do.
Sure, I think it's useful. It's not clear it's going to improve projections. You know, that's not demonstrated. But my exam question, what's the primary driver of the spread in those ISMIC6 projections? What's the secondary? What's the tertiary? You know, like, what's your list of, you know, what is the very first, the kind of main driver of the spread, you know, from negative to positive? What's second, what's third?
I think what they list is, of course, they have the surface forcing and the ocean forcing. So it's one of the major ones is what goes on between the ice sheet and the ocean interface. So calving, mainly in Greenland, but also like for the big ice shelves in Antarctica, what is the what happens and what is the mechanisms and how well can we describe it inside the model. So it's not, so that definitely several issues related to this spread, but one of the important ones is also how they are initialized and what sort of trajectory they are on when they start the present day simulations.
Okay, can I keep going just for a couple? I mean, we'll carry on tomorrow, but just like so SMOS, and I know Lars has worked on this quite a bit, but SMOS has been flying for 16 years, slightly more now. You demonstrated that actually you can get end glacial temperatures to some depth in SMOS with some probably not very good assumptions about the complex permittivity of the ice, but we'll come on to that maybe if we have time. Why haven't there been lots of studies and lots of work done on end glacial temperature with SMOS over the last 16 years then? There have been a handful, but not really, I wouldn't say, certainly the ice sheet modeling community haven't adopted them, and I mean, I don't see like big traction there. I know, Lars, you've done it for ice shelves, but like beyond that?
Yes, we did some work in ESA. I think we had 2 or 3 studies, and maybe Ghislain, for a change, you participated in the study. I think this is a very big question for the MAC to answer.
Okay. Yeah, so it's difficult to comment why the others have not done what we have done, or we'll try to do, but maybe the answer is CryoRad, because L-band is good, but it's not good enough, because the big difference is SMOS is sensitive, let's say, up to 1,000 or so 1 kilometer, but with CryoRad, what we hope to have is really the basal state, and for us, it's what is changing everything in the interest. So SMOS demonstrate that we can see deeper than the surface, but we know now that going to a lower wavelength, so a longer wavelength, is a game changer for the retrieval, and we'll get it's really a game changer in terms of product we can get. This is why we propose a CryoRad.
Okay, yeah. I don't want to get into the weeds here. One other, and this is like going back a long time. I may have misremembered a lot of this, but we've been doing ice penetrating radar or radio X sounding of ice sheets for like 70 years, since the 1960s. To do that, you need to know what the complex permittivity of the ice is reasonably well. There have been lots of studies over decades, Johari and Charette and Westphal, and all of those studies on complex permittivity of ice. I've done them myself. Why do you have to do this? I don't know what the appropriate phrase here is, but I'm surprised that you feel you need to redo this. These measurements of the complex permittivity. Now, like obviously it's frequency dependent, but above, it's a Debye dispersion, right? And then above that, you've got this Arrhenius relationship between temperature and frequency, and that's very well understood, right? But the permittivity is going to be a function of crystal fabric, impurity content, all sorts of things that vary in nature. So I don't understand why you're looking at this again.
Okay, maybe that's also for Ghislain to start with.
I can start
and then for Gwen to
answer. Because at P-band, we are in a very low absorption compared to all the other frequencies. And for us, what is key is to know exactly how is this minimum, and this minimum has not been explored so much. So you were talking about radio sounding, but it's not the same range of frequency. And to extrapolate, so the uncertainty we have at P-band is because most of the studies were either higher frequency or lower frequency. So we know to perfectly know the shape of this minimum in this range.
Okay, so and then how are you dealing with the variability that you get in space from natural variations in the ice fabric and impurity content?
So it's currently we are trying to
estimate the absorption of the pure ice. So most of the work is on the pure ice. And then, as you suggest, the ice inside the ice sheet is not exactly the same as pure ice. The crystal size is not the same. The impurity content is not the same. But the pure ice measurement we are conducting are fixing a level of absorption. And then we have also experiments or studies that tries to go from the observation we currently have from, for instance, with MOS or with LoMIRAD, and going back to the variation of this absorption. So we have two kinds of studies to investigate more about these variations. And we hope to know, like this, how it's changing, for instance, as a function on the transect in Antarctica between the coast and Concordia, for instance. So we will be able to really characterize all this change over time, over the distance, over the space.
There was one additional comment by Ji Wen.
Yes, Yiwen Zhou from the Swiss Federal Research Institute, WSL. So I think, although there are a lot of study work on the ice dielectric constant previously, but most of these studies are on the higher frequency, from 2 gigahertz to higher. And two of the widely used model, one is Metzler that we showed, and the other one is a Thury model. They have a big discrepancies, and Metzler, I mean, I know Metzler very well. We had several discussions, and he confirmed, like, he used his higher frequency measurements together with some other models developed by others to fit a Debye formulation. And the tricky part is there could be a temperature-dependent relaxation happen at P-band. And this actually temperature dependence is like the slope, you see the curve. And that's actually very important in the retrieved ice temperature profile. So that's why we think we have to understand this better. Yeah.
Eden?
Yes, I would like to move to the other objective of the mission, like the salinity and the ice sheet, the sea ice, sorry. And I have the same kind of question. I'm convinced, I'm not an expert, but that you will observe better salinity in cold water than before, and that you will have new information on the sea ice. But I'm not able to really articulate the science in terms of number, what we will learn from that in terms of big science question, and maybe not only using we can always improve models. That's true for all the compartments of the Earth system. When you have more data, we improve models. But then what would be the implication of having a better salinity estimate in cold water in a quantitative way, or precisely?
Okay, I think this is a question for the Copernicus services.
Not necessarily for Copernicus services, but the matter is the freshwater content in the Arctic. If you look at the trends, the studies, they're always expressed in anomalies of freshwater content towards a zero line that is not really well known. So there's, say, a large collection that AVI has collected of in-situ measurements. That's the best we have now to have the absolute freshwater content in the Arctic. But as you can imagine, the density of profiles in the Arctic is very low compared to the processes, the variability, and you integrate that over large areas, long times, and you're not really sure where is the freshwater moving. Is it is it increasing, decreasing? It is say today difficult and relies almost completely on in-situ measurements, which we don't know how they will change in the future. So CryoRad brings like a picture of surface salinity that I believe will become a reference in that freshwater dialogue. Maybe Jacqueline would bring some more.
Thank you. Jacqueline Boutin from l'Océan Climate Laboratory in France. So to complement what Laurent said, there has been studies using smooth and SMAP salinity in polar regions, in particular to better understand how the fresh water, where the fresh water goes within the ocean. And looking at fresh lenses that are created by the freshwater release. But one big limitation in these studies are the spatial resolution of the data we have today. And here we CryoRad combining the various frequencies, we should be able to improve a lot the spatial resolution of the present measurement. And another aspect is the influence of the low salinity data onto the sea ice formation, because there has been recent studies based on satellite salinity showing, for instance, that river plumes are precursor for sea ice formation. And for this, we really need to well monitor the low salinity regions, and the low frequency would be an advantage for that.
Another question? Yes, Marcus?
Apologies, I have one more question on the basal temperatures. I was convinced about the uniqueness of your observations until your last slide, or one of the last slides, where you showed that biomass is actually observing in this frequency range. Could you comment, please, on the, I mean, why we can't use biomass observations for looking at this quantity?
Okay, this clear question. I think it will be a clear answer.
Yeah, that is more clear than the other, because you know that active data are not sensitive at all to the temperature. But so we can benefit of having biomass so that they can provide information about structure of the ice sheet. So we can use this information for improving our understanding of measurement. But actives are not sensitive at all to the temperature, so we cannot derive with biomass such information. No, it's a radar.
Jonathan? Okay. Wait for the mic.
Yeah, hi, it's me again. I think you know who I am. Right, let's go for sea ice thickness. So for Lars. So looking at that plot you had of the area of sensitivity, you didn't show anything, and I realize that there's an issue around snow thickness with these, but ISAT2 gives you thickness right now, or freeboard at least, and the newly, well, likely approved EDGE, which will be even more, you know, its scanning LiDAR system, will give you very, very detailed freeboard in the Arctic. I looked at the CryoSat map for the Arctic, and there's also a lot of variability, particularly at the ice edge, in ice thickness. So your 50-kilometer resolution seems like a bit of an issue for ice thickness, particularly in the marginal ice zone. Plus, you know, areas like Baffin Bay, you've got, I don't know what happens with the land contamination and all that kind of thing. So can you kind of speak to that a little bit?
Yeah, thank you for this question. So first of all, so Lars Kaleshke from the Alfred Wegener Institute. So first of all, we use SMOS for this thick ice already, which has a similar resolution, and it gives unique and good information that helps us to improve the sea ice thickness estimates. And it's also not only about the Arctic. In the Antarctic, the data situation is much more sparse. We have the altimeters, which give good information, but we have the sparse sampling only. And in addition, there is a lot of snow on top of the ice, which makes difficulties with the retrieval with the altimeters only. And yeah, this is something where also CryoRad will contribute significantly, because we get the combined information also about the sea ice and the snow information together. Also, we have sensitivity to ice concentration, which can further reduce uncertainties.
Okay, and how does it work where you have like very thin grease ice and areas of open water in the same footprint?
It will give you the integrated value, that is the effective ice thickness or the ice volume. That is also an important climate parameter. So in this case, it's not really the sea ice thickness, it's more the effective thickness.
Any other question? Maybe online? It's a reminder for online attendees also that you can ask questions. No, nothing? Yes, at the back.
So we have had a long exchange about scientific justifications. Now I'm coming to the technical, more technical one. I think it was very good that you have a huge chapter on how to deal with natural emissions, and you have shown quite well what measures you can implement on this. I was quite fine with this until slide 98 of your presentation, where you come with a statement that non-natural emissions is quite, you are in an uninhabited area, and therefore it's not so much a problem. I think, if I got it right on the presentation, yeah, you showed that this is an area where non-natural emissions is not really a problem, yeah. But I think this is, to me, surprising, and maybe but I have to apologize, also a little bit naive, because in what we all know is that the polar regions have unfortunately shifted from natural scientific sanctuaries to prime areas of great power competition. And in 15 years from now, it already has started. We can laugh it on it, but we will have to face it. There will be a lot and a huge traffic, commercialization, resource extinction, and military outreach. Yeah? So there will be a tremendous increase of frequency spoofing, spoiling, and mobile communication. And what I would have loved to see, like in other models, when statistic on we have discussed it in Hydroterra on the first day, the effect of clouds. Yeah, so statistical effects of clouds. So what is the most likely setting of frequency spoiling in 15 years from now, and what is the limit you can deal with? Because if you filter it out and it's just an incredible noise, you have no signal at all left. So the slide on 98 was, for me, it was quite shocking, yeah, because I thought you dealt very well with the substance, but then you simply say it's not really a problem, and then problem solved.
I think this is a bit of a misunderstanding, because the technology is the technology. We have it for 1 megahertz, and we can deal with whatever will be there. But I'm giving the microphone to Roy,
Yes, Roger Oliva from Zenita Blue. So no, I guess that's been a misunderstanding. We clearly see that this is a problem. That's definitely something we're putting our focus on, and that we want to very much investigate. So what we were saying is that we know that the non-natural emissions will be everywhere, but they're mostly linked to human settlements, human activities. We're not saying that there are not going to be any in the poles. There will be. What we have is that with the development of the payload that's been triggered, we want to have very slice spectral resolution and very slice time resolution, so we can clearly filter out any type of emissions that there are. They're not going to be occupying all the band. The advantage of CryoRad is that we have 1600 megahertz and very simple, very thinly also with time, so we can recover. We expect we can recover a very large amount of data on the areas of interest. We obviously try to make some predictions of what's going to happen. We're studying very much what's happening today, so we have like a very good information of databases that we have been compiling of where there's emissions and how they affect and the powers and that we want to put into the simulator. But obviously, we don't know what's going to happen in 10 years from now when we launch, in 20 years, or if we're still running. So we want to make some extrapolation analysis on this aspect.
Okay, we still have 1 minute. So is there a last pressing question?
Only a remark. Reading in the report is a statement that launch of fairing is close to be eaten up by the feeds or by the antenna. Could make something worrying, because there's a statement that this may affect redesign of the platform and or the feeds, and redesigning in later stages is always costly. Yeah? So the mission should be very carefully to downsize the payload, like other missions did it in the past, where also in the very first stage they were at the edge of the fairing. So do whatever you can to miniaturize your payload, yeah?
Yeah, I think there's a comment on the comment.
Yes, it's working, yeah. This is well understood. So the feed has been sized to fit in the fairing, and the fairing envelope is really the hard limit with some margin. There will be no growth of the feed size. And if we had to shrink the feed size, this is very possible. There will be only a minor degradation on the directivity. And as you can see, in the phase 0, there was a full design, manufacturing, and test in 4 months. So the turnover to redesign slightly lower feeds is really fast. So the risk is really low. And in terms of the reflector accommodation, so the stowed reflector accommodation, so that has been sized. It's scaled from the CIMA size. And in phase 0, there will be a detailed FEM models in phase A, I mean. So at the end of phase A, we will have the exact size of the stowed volume. And again, there's margin right now with the fairing to the stow envelope. So there's a risk, but we see it as very small.
Okay, and with this last answer, so we can now close this Q&A session for CryoRad, and thank again to all the team. And so now we have a 30-minute coffee break, and so we will reconvene at 3:45 for last Q&A session. Thank you.